Hello there, my name is Charles Sipa. Welcome to a presentation which I've entitled here, The Mechanics of Differentiation. In this presentation, I'm not really teaching differentiation. I want to highlight some of the important things which one should take into account when you are differentiating a function. And the most important, when you are differentiating a function, I think the first thing to understand is the structure, or let's say the constituting part of a function. So let's start this way. Let's look careful at this kind of a function with independent variable x. This function is given as y is equal to x squared. You must understand this function as what I could call here a 2-power function of x. In general, I would write this as y is equal to x to the power n, which is an n-power function of x, where x is the argument of the function, and in this case the function is an n-power function, and then n-power function of x, which generally we write simply as x to the power n, or in particular x to the power 2 if our power is 2. Then now if we were to differentiate this function using the incremental quotient, this is what we'll do. We'll write y prime or dy dx is equal to the limit of the incremental quotient, which when we vary the function according to the action of the function on the argument, because in this case the function basically spells out the action on the argument. So here the action on the argument is squaring, so we square minus that, you get that. So moving forward, expanding this term, we would get the following. Expanding the polynomial, we get this, and then simplifying, noting that x squared minus x squared is equal to 0. Then we move to the next step, which takes us to the following. And then we've got here 2x times delta x plus delta x squared, which if we try to evaluate this function using direct evaluation, would get the independent form 0 over 0, which you cannot give as a limit. So what we'll do then, we'll factorize this and get this way. And simplifying this further, we can rewrite this as the limit of 2x plus delta x over 1 times limit of delta x over delta x. Recall here that delta x is different from 0, so we're not having 0 over 0 here, we just have this change approaching 0. So we can now apply direct evaluation to this part here, which will give us 2x, and then to this part here, basically we can look at it as a rate of change of x with respect to x, which we can actually interpret as a derivative of x with respect to itself. And we note also that delta x over delta x, which actually give us 1, and then the limit of 1 as delta is going to 0, wherever, it will be 1. So this is what we get next. We have here that this limit, we can write it as dx over dx, which is 1. And then when we write it this way, we'll interpret it as a derivative of x with respect to x. So then we can then now look at this derivative of x squared as 2x multiplied by the derivative of x with respect to x, which in this case will be the derivative of the argument. And that is important to note. Then we're simplifying this, will give us 1, and we usually write our answer as simple as that. But we must never overlook that every time when we differentiate, we also need to differentiate the argument of the function. We will see this more explicitly later. Okay, moving forward, in this case now looking at the trigonometric function sine. Again here we've got sine of x, which you can write this way, just square bracket to emphasize or to highlight what is the argument, which in this case is x. And then when you come here, you can actually identify sine as the function, now it's the action on the argument x, then write this as f at x. So in this case here, when I'm talking of function, I'm talking of sine. So it's sine of x is f of x. To calculate the derivative, you have to evaluate this incremental quotient and calculate its limit. And using trigonometric identities, we saw that we could simplify this and write it this way. And then the next thing we should notice here that is delta x is approaching 0 from both sides of 0 from the left to the right. The sine curve would actually approach 1. This then takes this kind of situation where we consider that the x cosine delta x approaches 1 is equal to that, then the difference between sine x and cos delta x and the sine x will be negligible as x is going to 0. Then the delta x is going to 0. Then this takes us to this form because we simplify these two. Then we get this one. Then again here we notice that cosine x does not depend on delta x. Using again the laws of limits, we can take this cosine x outside the limit and then calculate this special limit, which we know already that is equal to 1. Then we can now, looking only at this limit being equal to 1, we can again interpret that one being as a delta as dx, which is derivative of x raised to x. Then we can look at this derivative of sine as cosine multiplied by 1, where 1 plays the role of being a derivative of the argument of the function, which is cos. So it's a derivative of x with respect to x. So then it is important to understand how to do differentiation, what I literally call here mechanics of differentiation. We must understand the structure or the constituting parts of the function. We must also know that there is practically a finite number of different types of functions, and the functions themselves are infinite, resulting from different combinations of the finite different types of functions. So if we write this way, is y is equal to f of x. I'm going to explain soon why this syntax is used this way to denote functions in general. So in this case here, y, first of all, I think you notice here that we are in the presence of two variables, the variable x and the variable y. In this case here, y is the independent variable, and x, in this case here, y is the dependent variable, and the x is the independent variable. So in other words, to get the value of y, we must have freely chosen x in the domain of the function, and then f, the action itself on the argument, that will be the function. That's how you should understand the structure or the constituting part of a given function. So the reason why in general functions are given in terms of y is equal to f of x or y is equal to f of t is because our functions, we normally plot them on this Cartesian system of coordinates, the xy system of coordinates, which we can put this way. And what is important to understand here is that if you are at any point of the graph of the function, that point always got two coordinates, x, y, where x is the projection of this point to the horizontal axis. X will be sitting there, and the y is the projection of the same point on the vertical axis, and so y will be somewhere there. Now y defined this way, then y will be simple f of x, whereby we must understand that this point here is simple x comma f of x as a point on the graph of the function. That is very important and very useful to understand, especially when you're going to also find things like the equation of the tangent line or the normal line to a point at a given point, x. So moving forward, now these basically give us the kind of finite types of different functions. For example, we can have a function here, f, having function written in y is equal to f of x. The function could be a polynomial, which is a function which generally gets an expression like this, or it could be a trigonometric function, a sine, cos, or tan of any argument, and then, for example, in particular with sine x there. And you can also have an exponential function, which you can also denote this way as exp of an argument, but in generally, or in usually, we use this shorthand, which is a to the power of x, for the exponential function of x. So you should notice here that this is basically the name of the function, exponential of x, just like the name of the function is sine of x. So sine is an action on the argument x, and here the exponentiation is an action on this argument x. In general, also, you can take any base a greater than 0 different from 1, because if it's equal to 1, it will give us a constant function, which also falls in these types of function. So we can write y is equal to a to the power of x. And then the other type of function we've got is the logarithm function, which in this case are the inverse of exponentials. The logarithm natural base is just simply written as ln x, but you must know that when we got this code, it means logarithm function base e. In other words, we replace a by e, then we get this kind of function. But in general, this is the logarithm function. And in addition, you can create more functions by, for example, taking powers of all the type of functions, the different combination of this type of function. So we get more functions this way, and we end up basically with an infinite functions. It could be a power of a trigonometric function or a power of an expression like this. That's it. So then now we move forward to explain exactly what goes on when we're differentiating type of functions, which we've seen here in this previous example here, these two examples, and this very first one. So what I'm going to do now is, let's say we're given a function y is equal to sine of x squared plus x. Now notice the structure which I'm talking about is that now here the function is given as y named sine of the argument. In this case, you have to understand that the argument is by its own right a function. So now this is a sine of another function. So having this kind of a situation, we must sort of create a hierarchy here, because we've got more than two functions involved. Here we're saying y is equal to sine. Then I'm going to use the term here, leading function. So y is the leading function, sine. And then the next function, which is an argument, is a polynomial function x squared plus 1. So it is a function by its own right. So now if we were to differentiate this, this is what we do. This is actually what we have seen. We'll simply write dy dx is equal to cosine x squared plus x multiplied by 2x plus 1, which is the derivative of argument. So what is involved here is that when I'm given a function, trigonometric function sine, if I were to get the derivative of this function with its argument being another function like that, what simply I would do, I would evoke the derivative of sine, or the immediate derivative of sine, which is cos, retain the argument. Now let's keep the argument exactly as it was in the original function, but multiplied by the derivative of the argument. When you've done that, you've actually done the complete derivative. If you want, here you can still look at x as the argument of this polynomial function, so it will be actually fit also here to say dx. But in general, this we don't write, because 1 is actually a neutral element for multiplication. But for explanation, you must understand that your differentiation is carried out until to the simplest argument, which differentiates to 1 as dx equals to 1, where actually this is a derivative of a function y is equals to x. So this will be the simplest argument of a function. So having the above type of understanding of differentiation, we can create ourselves this kind of mantra for differentiation, which says, given a function, the derivative will always be the derivative of the leading function multiplied by the derivative of its argument. Always keeping in mind that the argument by right is a function, which in its simplest form, it is the independent variable x or t, depending on what we're doing, whose derivative is the unity 1, as 1 equals to dx dx, or 1 equal to dt, depending on what is the independent variable of your function. So I hope this will help you to understand how you differentiate. And also, when we do implicit differentiation, this is very important to understand how you differentiate the function, because if you don't differentiate the argument, then you might get your derivatives wrong. So I re-emphasize that please go through this presentation again until you really understand what is it, what does it take to differentiate a function A function could have a simple argument, or a function could have a kind of a complex argument as a function itself, as compared to just sine x. You must know how, you must be careful with how you carry out that kind of differentiation. So at this point, I would like to say thank you for listening. Please enjoy your practice of differentiation, and keep this kind of understanding very fresh at your fingertips, because it is also going to be very, very useful when you get to integration. Bye for now.